um, what we are going to do is basically we have like maybe I forgot how much I calculated. So 8-9 hours of class left. So what I am going to do now, we are going to study a particular kind of nano material or nanostructure, which is known as carbon nanotube. And we will see like how carbon nanotube based MOSFET is made, or a structure wise carbon nanotube based MOSFET, how it looks like and how it operates. Okay, now apart from that, we will also cover uh, um, characterization equipments, because we haven't covered any characterization equipments. For example, we will cover scanning electron microscope. Optical microscope is not good enough to um, see or visualize nanostructure, because in optical microscope you see the visible wavelength is around 400 to 700 nanometer, whereas uh, it might often be the case your nanostructure is much smaller than that. So optical microscope is not good enough. We use a scanning electron microscope, or ACM. So instead of light, we use electron to see the surface morphology of the nanostructure. So we will study ACM and some other characterization equipment after discussing carbon nanotube. Okay, so so that will take quite a few classes, and then we will see if we have some time what else we can cover. Okay, so so for the time being I'm going to cover carbon nanotube and carbon nanotube based MOSFET, and then we will cover the different characterization equipment. Okay, so I think in next half an hour or so I will cover the basic carbon nanotube part, and the maybe the FET part I will cover tomorrow. Okay, I mean the carbon nanotube based FET. Now carbon nanotube is also known as carbon nanotube is also known as CNT. In brief, it is known as CNT. So as the name suggests, the structure is like a tube. Okay, the structure is like a tube. Of course, it is made of carbon. It is an allotrope of carbon. Okay, allotrope of carbon. By allotrope, we mean like allotropy is a property of some chemical elements to exist in two or more different forms. Okay. For example, there are several allotropes of carbon, right? Carbon can be probably many names you know. One is like diamond. Diamond is a form of carbon. Okay. Um, Here carbon atoms are bonded together like a tetrahedral structure, tetrahedral lattice structure. There are other allotropes like graphite is an allotrope of carbon. Okay. For example, graphene is an allotrope of carbon. Uh, there is another known as fullerene. Fullerene is an allotrope of carbon. Okay. Um, in graphite, it is like a hexagonal sheet. Hexagonal sheet. Okay. So this is like hexagon in graphite, and there are several hexagonal sheet on top of one another connected by weak van der Waals force. Okay, weak van der Waals force. Van der Waals force, right? So my drawing is not good. If I draw like this, so there is maybe another layer and so on, and these layers are basically connected through van der Waals force, okay, in graphite. But if you manage to remove, and if you have only one layer of graphite, or mono layer of graphite, this is known as graphene. Okay, so single sheet of graphite is basically graphene, single sheet of graphite. Okay, then fullerene is basically carbon atoms are bonded together in the form of buckyball kind of structure, a ball kind of structure. Okay, that is fullerene. Then of course there is CNT, that is carbon nanotube. It's kind of a cylindrical nanostructure. Okay, cylindrical nanostructure. Um, so these CNTs will form if you roll graphene. I mean, you will not be literally roll graphene. So graphene is basically a sheet. If you roll it, okay, you will form a tube. So that's basically your carbon nanotube. Now carbon nanotube maybe I mean, it's usually of two types. One is uh, multi-wall carbon nanotube, multi-wall CNT. Another is single wall CNT. Okay, so this is multi-wall CNT, and this is single wall CNT. Right. So when you rotate a single graphene layer and form a tube, it is basically a single wall carbon nanotube. But if there is multiple walls, then it is multi-wall carbon nanotube. Okay, and there are various kinds of radius and length depending on how you are fabricating it. Okay, length may be few hundreds of nanometer to even few micrometers length. Okay, and radius in case of single wall, radius is very small, maybe at max like few tens of nanometer. Okay, even less than 10 nanometer radius. Whereas in case of multi-wall, it's little bit more wider. Maybe again this can be as low as few tens of nanometer to hundreds of nanometer. Okay, but lengthwise usually quite long. Okay, again as I'm saying, it depends on how you are making it. Okay, your recipe of fabrication play an important role in the carbon nanotube length and radius. So carbon nanotube has like sp2 hybridization or sp2 bond. So it is much stronger than even that of diamond, because diamond is sp3 bonds. I don't want to go in that direction because that is again hardcore chemistry. And so just remember that carbon nanotube has like sp2 bonds, and sp2 bonds is more stronger than sp3 bonds, so it's more stronger than diamond and all that. Okay, so carbon nanotube, there are various applications. Okay, When carbon nanotube first came, it was discovered around 1991, okay, by Ijima. 1991 by Ijima. Um, Initially, it was thought that it will replace silicon because it has astonishing several astonishing properties. Okay, especially carbon nanotube, through which mobility can be very high, because the carrier, when they move through carbon nanotube, scattering is very less. So transport, we can get almost ballistic transport, that is, scattering is very less, so we can get much larger mobility than that of silicon. Okay, but having said that, since I mean, although it is first discovered around 1990, but parallelly we talked about that silicon microelectronics or silicon nanoelectronics improved quite a lot, right? So carbon nanotube failed to replace silicon, but it has lot of advantages. So we use carbon nanotube for different purposes. For example, carbon nanotube can be used as sensor. Carbon nanotube can be used as microwave absorber. It is a very good microwave absorber. Okay, so you can put carbon coating on military vehicles to avoid detection uh, using microwave. Carbon nanotube can be used as via as connector, like I talked about. And at the beginning, I talked about, like, in CMOS there are multiple metal layers, right? And multiple metal layers are connected through via, right? So those vias can be made of carbon nanotube, right? Because it can have a very large aspect ratio, very tall. As I said, like, it is as long as 1 micrometer or so, the length, and the diameter may be few tens of nanometer, even less than tens of nanometer. So it has various applications which people concentrated rather than replacing silicon. People have also developed carbon nanotube based FET, which we will discuss tomorrow's class. Uh, but you see, still we are not close to replace silicon, because the fabrication is not easy. It is not easy to make carbon nanotube on a specific area of the wafer, like we can easily do it in case of silicon based FET. It is not easy to make a single carbon nanotube in a specific position of the wafer, right? So that makes things very difficult, right? So let's go through some of the things, how we can make carbon nanotube and all that. um, I have a PPT to share with you. uh, mm, so this is a schematic representation of carbon nanotube. You see, as I said, like, hexagonal structure is there. This hexagonal structure is nothing but a graphene structure. Okay, and you can roll a graphene sheet to realize a carbon nanotube. Okay, and there are different way to represent it. I just don't want to again go in that direction. There are two indices known as N and M. These N and M indices represents what kind of carbon nanotube it is. It can be zigzag type, it can be chiral type, it can be armchair type, depending on due to rolling, how it is, how these M and N indices basically numbers we are getting. Okay, let's just and depending on this orientation, okay, the property of carbon nanotube changes and all that. So this is what I tried to draw, but I couldn't draw. So these are graphite material. Okay, and in graphite you see there are six carbon atoms, okay, in the hexagonal form, six carbon atoms, and each layer it is basically stick together through weak van der Waals force, and you can detach these layers by various techniques to get graphene. So each layer, if you can detach a single layer, it will form a monolayer graphene. Okay, and then you can roll it to form nanotube. For example, this is single wall carbon nanotube, few nanometers. Okay, though I mentioned 10 nanometer, few nanometers it is saying single wall carbon nanotube, but for multi wall carbon nanotube, the diameter is few tens of nanometer. Okay, this is fullerene. Fullerene is, as I said, it is a buckyball kind of structure. Okay, and it is diamond. Diamond is sp3 hybridized, whereas graphene and carbon nanotubes all are like sp2 hybridized, so they are more stronger than that of diamond. Now, uh, there are different techniques through which carbon nanotube can be made. One of the technique is known as arc discharge technique. Okay, arc discharge method. In arc discharge method, this is the method which basically IGMA used, okay, to develop carbon nanotube. This is almost a you do it in an inert atmosphere. This is like a graphite electrode, and you basically apply high voltage which will create high electric field, and discharge will happen, and carbon nanotube forms on the electrode. Okay, later on you can take those carbon nanotube and see it under the microscope how it looks like. If I get time, I will show you the carbon nanotube how it looks like, maybe in the tomorrow's class. I think I tried to find out the PPT, but I couldn't find the exact PPT. This is not the PPT which I usually show, but I will see if I can get the PPT tomorrow. So this is arc discharge technique. There is another method known as laser ablation method. In laser ablation method, in arc discharge technique, you need quite a high temperature to perform this. In case of laser ablation technique, here also high temperature required. In fact, here temperature is even higher. You need around 1200 degrees centigrade. You put it in a furnace. Okay, there is a tube. This tube has several components. One of the component is laser, okay, because it's laser ablation, and niobium, yttrium, aluminum garnet laser. And this laser, through this laser you bombard a graphite target. Okay, and there is a argon gas flowing inside the chamber, and that argon gas is basically taking whatever graphite is releasing because of this laser bombardment. And this argon gas takes this graphite particle in a water cooled copper. Okay, so this is the water cooled copper. When this graphite particle deposited on the water cooled copper, it was found that it is form a carbon nanotube. This particular process is not a very high yield process, but you can get a very high quality CNT simply because you are using very high temperature. Okay, um, so there is another technique which is known as CVD, okay, chemical vapor deposition technique. This is a technique which is used heavily in commercial industry. I mean, whatever carbon nanotube if you buy from the market, mostly it is CVD grown, because you can grow quite a lot. I mean, the amount will be very, very large, and also the accuracy wise or the purity wise is not that bad. Okay, although it is not as good as laser ablated carbon nanotube, but it is much better than arc discharge technique. Okay, so in this CVD chamber, what we have, like we have a gas in the form of, say, for example, C2H2, which basically dissociate. So what we have, like we have a substrate or a wafer. On that wafer we deposit a metal coating, for example either iron or nickel or cobalt. That metal coating we need to heat up. So you see this is a heating chamber. Okay, this heating chamber, inside the heating chamber we keep the wafer or the substrate coated with iron, nickel or cobalt. Those are basically catalysts or a combination of those. And at high temperature those catalyst form small islands. So those small islands are there, and then you pass a carbon gas, for example C2H2, along with ammonia and argon. Okay, ammonia basically helps in dissociating C2H2. So at high temperature C2H2 dissociate, and they push basically those small island to form carbon nanotube. Okay, so C2H2 will dissociate, and those carbon particle will basically push those nano island upward to form carbon nanotubes. So, and there are ways to you can keep those iron, nickel or cobalt nanoparticle on top of carbon nanotube, or you can remove them. There are ways to remove them. Okay, so here it is written that growth process temperature, you need to ramp up this heater. You keep this heater at a particular temperature for several minutes, and then you cool it down. Okay, so so there are mass flow meters or mass flow controllers. It will control the amount of gases passing going inside the chamber. Okay, and there are temperature controller and all that. Um, so apart from chemical vapor deposition technique, there is another technique known as PECVD, that is plasma enhanced chemical vapor deposition. In plasma enhanced chemical vapor deposition technique, instead of using at very high temperature, here you use quite a high temperature, maybe 700 to 800 degrees centigrade. Here you have to use. So if you don't want to use high temperature, because it might happen that the wafer or the substrate you are using might not be able to sustain that much high temperature, so then in that case you use plasma enhanced chemical vapor deposition technique. In this case, instead of high temperature you use plasma. Those plasma will basically break your carbon gas. Okay, that is acid C2H2 or some gases of that form, and it breaks that gas, and that gas then allows us to accumulate and form a carbon nanotube. Okay, so here I said here hydrocarbon can be broken with plasma instead of using high temperature. It is possible to get vertically aligned carbon nanotube in this particular case, because here you are applying electric field. Okay, however, one might get defects in the CNTs because here the temperature is much lower, maybe 200-300 degrees centigrade is good enough. So if you don't use high temperature, there might be defects in the carbon nanotube. Okay, so low temperature growth is possible, but there might be defects in the carbon nanotube, right? So yeah, so I forgot. So these are some of the images of carbon nanotube. For example, this is MWCNT forest-like structure. Here you see vertically aligned carbon nanotube. This is single wall carbon nanotube. So these nanotubes, as you see, it is not easy to form a single carbon nanotube. Okay, and it is not easy to form a very specific place. So that is why it is kind of difficult to compete with silicon based FET. Okay, whenever you grow carbon nanotube, you will grow it in bunch. Okay, then nowadays there are ways to form single carbon nanotube, but still it is nowhere near to silicon based FET, where you can accurately make a FET in a specific area of a very large wafer. Here it is not exactly the case, right? So let me just summarize whatever we have mentioned. Like arc discharge technique, it's very high temperature, Okay, whereas laser ablation you can get around 1000 1200 degrees centigrade. Both the cases yield is low, okay, but the quality is quite good in case of laser ablation technique. um, um, in case of thermal CVD, you see yield is very high. Okay, you get quite a lot of carbon nanotube. That is why when you buy carbon nanotube commercially, it is mostly thermal CVD. Okay, and temperature required around several hundred degrees centigrade, close to 1000 degrees centigrade. Whereas in case of PECVD, you can have like carbon nanotube even in 200-300 degrees centigrade, as I mentioned, but the yield is low, and also purity is not that good, okay, in case of PECVD. So this is a table just to summarize what kind of which process will give what kind of carbon nanotube. Now so there are many options to optimize the process. Okay, as I mentioned, there are catalyst, iron, nickel or cobalt. You can use single catalyst, you can use multiple catalyst, mixing of two or more catalyst. So catalyst thickness matters, okay, surface roughness matters, and so on. Then there are temperature, the chamber pressure, chamber, how you are ramping up the temperature, what kind of gases you are using. For example, I talked about ammonia. There are other recipes also. Ammonia helps in dissociating that carbon like gases, okay, and so on and so forth. So there are opportunities to optimize things. Different labs and they have their own recipes to develop carbon nanotube depending on their needs. Some prefers very high purity carbon nanotube, some prefers low temperature growth, some prefers defects carbon nanotube. For example, if you want to use carbon nanotube for sensing purposes, for example gas sensor, there you need carbon nanotube with defects, because the defects in the defect places the gas molecule will attach. So those defect places will act as a active sites for the gas molecule to attach. By defect I mean maybe some carbon molecules are missing, okay, so that is a defect, or some other material is attached to it, okay, so that's basically defect or functionalization. So that kind of, so depending on the requirement. But if you want to go for electronic devices, your carbon nanotube has to be has to be purer, okay. So these are depending on your requirement, you make carbon nanotube. Overall it is a high temperature process, okay. Yeah. Now so this is uh, here. From here we'll talk about fate based structure of carbon nanotube. I think I will start this particular part in the tomorrow's class. So we will talk about backgated CNT FET, that is the gate is from the back side, and CNT is basically acts as a, or carbon nanotube acts as a channel, okay. It is not like conventional MOSFET where we have like two source and drain, which is like say N plus or P plus, and there is a channel portion which you need to invert and all that. Here the working principle is different. We will talk about working principle in tomorrow's class. But the carbon nanotube itself acts as a channel, okay, itself acts as a channel, and of the FET. And you will have like source and drain, just metal contacts will act as a source and drain. And for example, this is back gated CNT FET, so the gate is from back side, okay. You can have like top gated CNT FET also. So gate will be at the top. This is like conventional MOSFET type of structure. We can have like gate all around CNT FET. You remember during FinFET we talked about gate all around. If you have like gate all around, you will have better control. How we fabricate this, again we'll talk about this in tomorrow's class. And then there are other FET like structure, which is like suspended CNT FET, where CNT is suspended. Okay, so it is not directly on the substrate, so you see there is a air gap between the substrate and the CNT, so it's like floating or suspended. Okay, and so on and so forth. So there are different kinds of CNT the structure FET structures. We will discuss this in tomorrow's class, right? So you have any doubt? Do you have any doubt? You don't have any doubt. Okay. So so we are closing the class now. Then today we will discuss in detail about the CNT FET tomorrow, and also its working principle. Then we will start the different characterization equipment. Okay. Precisely, we will cover, I think I'm planning to cover ACM, that is a scanning electron microscope, XRD, okay, that is X-ray diffraction technique, okay, and XPS. I think these three we will cover, and also AFM, definitely AFM. So these four I am planning to cover, and then we will see how much time we will have. Okay, okay. So thank you very much. So once I manage to block the slot, book the slot in Moodle, I will let you know about the exact date and time of the quiz. But this probably either 4th or 5th. Okay. Okay. So thank you very much.